Hello everyone. We don't have a new lesson today. We just have this first example, which was based off of yesterday's big idea. So just practicing another example using the first part of the fundamental theorem of calculus. And then in the rest of this video, I'm just going over the problems that I assigned yesterday, and then I'll give you some more review problems as well. So based on yesterday's big idea, given that y is equal to the integral from 4 to t of 5x to the fourth dx, find dy over dt. So pause the video to give this a try. All right, and if you need more time, pause the video again. Now dy over dt is just y prime. So again, it's the derivative of this integral, which is the derivative of the antiderivative. So dy over dt should just come out to be 5, but notice the x and t are reversed, and that's okay. So it's just whatever variable is up here is going to replace this. Now, if you wanted to, you could evaluate this integral and then take the derivative of it, but it should bring you back to 5t to the fourth. All right, so let's take a look at each problem that I gave you yesterday. Most of them I have the answers with the explanations already posted, but for some of these I will be writing them in as I go over them. So let's start on page 257, number 26. All right, we're given an image in this graph off to the right here. It says the graph shows the sales record for a company over a 10-year period. If sales are measured in millions of units per year, explain what information can be obtained from the area of the region and why. Well, we know because this is just one region, it would calculate total area, or we've also calculated total distance traveled with just one area like this. But in this context, it is looking at the total number of units sold. So the area of the region is the total number of units sold in millions over the 10-year period. Now, the reason I know it's in millions is because the area units are millions of units per year times the number of years. So the years cancel out and we're just left with millions of units. And that comes from the problem because it says sales are measured in millions of units per year, and then we multiply by the number of years. So that's why we're just looking at millions of units. All right, next we have page 268, 43, and 45. All right, we're asked two things for these two problems. We want to first find the points of discontinuity of the integrand. The integrand is the expression of what we're taking the integral of. And B, use area to evaluate the integral. So for 43, if we look at this expression, we know that denominator can't be 0. So it's discontinuous, I have this written over here, at x equals 0. Now to get the graph of this, for any positive x value, I would just have x over itself. So that would just always come out to be a 1. So that's this top part. Again, it's discontinuous at x equals 0, so I have open endpoints here. And then when x is negative, I'll still get a positive value because it's the absolute value, so I'll have a negative 1. So this is what the graph will look like. And then I just want to start and stop this from -2 to 3, so I create two rectangles. So the area of the first rectangle would, because it's below, is -2 times 1. Remember, I'm not asked to find area, I'm just using area to evaluate the integral. And then the second rectangle has dimensions of 3 by 1. So that's -2 plus 3, which is 1. For 45, this is the integral we're given. Right here in our denominator, x cannot equal -1. So this is discontinuous at x equals -1. Then I could simplify this fraction by factoring the numerator, so this turns into just x minus 1. But I have a removable discontinuity at x equals -1. So notice the hole that's right here. So I'm just graphing the line x minus 1 with this removable discontinuity right here. And I create two triangles. Now, I didn't write out their areas, but if you found these two, again, the first area we would make sure it's negative, second one is positive, and the result should be -7/2. All right, next is number 28 on page 275. Here we're asked to find the average y value of the function on the interval that's given, so we're from 0 to 3, and at what point or points in the interval does the function assume its average value. So let's remember the formula. we'll say the average value, I have the answer here, it should turn out to be 1 when x is 0 and 2. So you could write them as ordered pairs, or you could just say when x is 0 or 2. So the average value is equal to 1 over the distance between this, so we'll start with 3 minus 0, times the integral from 0 to 3 of x minus 1 squared dx. Now there is no chain rule for integrals, but what we can do, we have no other option here, but we can expand this. So we're going to get 1/3 times the integral from 0 to 3 of x squared minus 2x plus 1 dx. And now we could take the antiderivative of each term. So we get 1/3 times x cubed over 3 minus 2x squared over 2, so this will just turn into an x squared, plus x from x equals 0 to 3. So now we'll get 3 cubed over 3 is 9, 27 over 3, minus 3 squared is 9, and then plus 3. Now we always want to write this in here, but we will get a 0. 9's cancel, 1/3 of 3 is 1, so the average value is 1. Where does this occur? Well, we'll just set this expression, x minus 1, that quantity squared, to equal to 1. Take the square root of both sides, we'll get plus or minus 1 equals x minus 1. So x is going to equal, if we went with a positive 1 plus 1, because we're adding 1 to each side, we'll get a 2. Or x is equal to a negative 1 plus 1, which is 0. So again, you could write the ordered pairs, or you could just say the average value is 1, and that occurs when x is 2 and 0. And both of them are on this interval, so we're good. All right, next is number 8 off of page 295. All right, so this one deals with, they gave us a nice little diagram here for stocking a fish pond. As the fish and game warden of your township, you're responsible for stocking the town pond with fish before the fishing season. The average depth of the pond is 20 feet. Using a scaled map, you measure distances across the pond at 200-foot intervals, as shown in the diagram. A, use the trapezoidal rule to estimate the volume of the pond. So remember, volume is length times width times height. So we have this, the depth here in green, which is the 20. So that's kind of like the height. And we're going to use a trapezoidal rule. So we start with 1/2, and then the increments here measure every 200 feet. So that's going to measure 1 dimension. So really we're finding the area of the base times the height, which is this 20, or the average depth. So we have 1/2 times the 200. And then our first value starts at 0, and then we double every value in between till we get to the other end, which is 0. So we calculate that, and we get this 26,360,000. Now part B, you plan to start the season with 1 fish per 1,000 cubic feet. So that's why I have 1 fish per 1,000 cubic feet. You intend to have at least 25% of the opening day's fish population left at the end of the season. What is the maximum number of licenses the town can sell if the average seasonal catch is 20 fish per license? So we're going to take this 1 fish per 1,000 cubic feet, and then we want to apply it to the entire volume that's here. So we multiply it by the volume, and then that just leaves us with 26,360 fish. And we're going to take 1/4 of that off, because that's how much we want to just leave at the end. So that means during the season we'll have 19,770 fish, and then we divide that by the 20 fish per license, and this comes out to 988.5. So we could cut it off at 988. So the max number of fishing licenses is 988. All right, now on page 297, number 22, I actually want you to go back and explore Simpson's rule. This is on page 292 of section 5.5. And this is it written out. But if you use the trapezoidal rule, you got the same thing. But I want you to go back and read over Simpson's rule. It's just a slightly different formula. So this deals with wing design. The design of a new airplane requires a gasoline tank of constant cross-section area in each wing. A scale drawing of a cross-section is shown here. The tank must hold 5,000 pounds of gasoline, which has a density of 42 pounds per cubic foot. We want to estimate the length of the tank. And then all the y values are given to us, and it says horizontal spacing is 1 foot. So that's why we're able to use this. But if you used the trapezoidal rule, you'd start with 1/2 times 1, and then you would go through the process there. Now to find the length, we take the 5,000 pounds, and then we need to convert it. So, because we're trying to get length, which is in feet here. So we take the converting unit here, which is 1 cubic foot. We kind of invert it for every 42 pounds. So that's going to get rid of the pounds. Well, we want to end up with just feet, not cubic feet, not square feet. So we would just take that. This is the area that we found. And then we would take and divide by the 11.2 square feet. So now we're just ending up with the 10.63 feet. So regardless if you use Simpson's rule or the trapezoidal rule, you'd still have to do this part of it. All right, and then the last problem, page 300, number 54, is quite a few parts. This is a lot like the second example we did in class yesterday with this big idea. So I want to read over the parts. Please refer back to the graph that's given to us. Actually, I'll go ahead and make a sketch of it now. All right, so the graph of a function f, so this is y equals f of x, consists of a semicircle and 2 line segments as shown below. Let g of x, what I have up here in red, is equal to the integral from 1 to x of f of t dt. So for part A, we're asked to find g of 1. So g of 1 just becomes the integral from 1 to 1, and we really don't need to say any more. As soon as those values are the same, we're always going to get a value of 0. For part B, they want us to find g of 3. So this becomes the integral from 1 to 3. So we're looking at really the area of this triangle, but because it's shaded below, we're going to make that negative. So I have this just written out on the next page. So it just becomes negative 1/2 times the base times the height, so we get a negative 1. For C, g of negative 1, I'm going to go back to the other page, shows it right here. G of negative 1 becomes the integral from 1 to negative 1 of f of t dt. But I need to flip that because I want my numbers to go in order. So if I flip the limits of integration, remember I need to take the opposite there. So now this becomes the opposite of the integral from negative 1 to 1 of f of t dt. Now if we go back to the graph, negative 1 to 1 makes a half circle right here. Actually half of the half circle. So we're at a quarter of a circle. So I have 1/4 pi r squared, but it's negative because I had to pull that out or take the opposite when I flip that. So we get negative 1/4 times pi times 4, so we're at negative pi. So that's the value for C. Question D, find all values of x on the open interval from negative 3 to 4 at which g has a relative max. So we know if we look here, we have the max area at 1 when x is equal to 1. Or, and again, I want to make sure you're able to explain it. So you could talk of this in terms of area or how we worded it in class yesterday. G has a relative max. This is crucial. We want to connect those two. When g prime of x is equal to f of x, and that changes from positive to negative. So this happens when x is 1. So here f of x is positive. It turns to negative here. Question E, write an equation for the line tangent to the graph of g at x equals negative 1. So we need to find the slope of our tangent line at x equals negative 1. So that's indicating g prime of negative 1, which is also equal to f of negative 1. Because remember, g prime of x is equal to f of x. And that's the slope of our tangent line. So if we go back to the graph, f of negative 1 is right up here at 2. F of negative 1 is right up there at 2. So this is equal to 2. Then we need to figure out what g of 1 is, because we need the ordered pair. Sorry, negative 1. Negative 1 comma what? So we already calculated g of negative 1. G of negative 1 was negative pi. So our ordered pair is negative 1, negative pi. Now we have the slope of our tangent line. We have the point where it's tangent to the curve. So then our equation becomes y minus y1, so it becomes y plus pi, which is equal to our slope times x minus x1, so x plus 1. And we can leave it just like that. Question F. Find the x-coordinate of each point of inflection on the graph of g on the open interval from -3 to 4. So right here, what I have explained, the point of inflection occurs when our second derivative, so g double prime of x, which is equal to f prime of x, changes sign. It's not specifically asking for concave up or concave down. We just need to see when our second derivative changes sign. So we make a second derivative number line. Now remember, we're looking for the slopes of the tangent lines on our graph. So let's go back to our graph. Everywhere from -3, and technically -3 and 4 are the endpoints on our number line. Everywhere from -3 to -1, we have positive slopes. Then we switch to negative slopes. Then we're still at negative slopes up to 2, and then we turn back to positive slopes. So the signage here is plus, minus, minus, plus. So we have 2 times where it changes signs. So we have points of inflection at x equals -1 and 2. And then the last part is asking us to find the range of g. Now we have critical numbers here. So remember, now we're on a closed interval as well. So I'm going to go back to talking about this part. So if we're on a closed interval, we're actually going to have an absolute max. Now we saw that the relative max occurs when x is equal to 1. So we know the absolute max is g of 1 is equal to 0 from part D. Well, we have critical numbers here. If we took a look at the graph, it's where our first derivative, so where our graph is either undefined or equal to 0. So that happens. We have the endpoints at -3 and 4 as well. Our graph is equal to 0 at 3, which we found g of 3. At 1, we found g of 1. At -1, we would actually have our second derivative, so the slope of our tangent line is 0. We found g of -1. So we need to find some other values. We need to find g of -3, which I have right over here. We need to find g of 4, which I have right here. And then also talk about g of 2. So let's talk about let's go with g of 2 first. G of 2 is going to be the integral from 1 to 2 of f of t dt. So that's cutting this off right here. So that's just going to become, it's below the x-axis, so we have a -1/2, and then we have a base of 1 and a height of 1. So this is just going to give us a -1/2. So these are all the outputs. So we're just trying to get all the outputs together so we can see what is the smallest output, what is the greatest output, and that's going to mark the range. Now g of -3 is the integral from 1 to -3 of f of t dt. We need to flip that, so we go from -3 to 1, so we put a negative out in front. Now -3 to 1 is a semicircle, but we make it negative, so we take 1/2 of pi r squared, so we get -2 pi. So right now, other than the 0, it doesn't look like we're getting any positive values here. So let's check g of 4. So g of 4 is the integral from 1 to 4. So what I did was I took the integral from 1 to 3, which was g of 3, and that was -1. And then I added it with this other little area, which would be right here, and that would be another 1/2. But -1 plus 1/2 is -1/2. So it looks like our values go as low as -2 pi up to 0, and that is the range of g. All right, so it would be I would highly advise you to go back over these problems at least 2 more times. You don't have to do them all tonight, but just from now until the test and even before the AP exam, just start to review them again. So here's another set of problems. And I'll have these posted as their own section from the textbook. Now, what I did decide, what I mentioned, I don't know if I mentioned it earlier, I am going to push the Chapter 5 test back to next Wednesday. So as always, guys, take care. Let me know if you have any questions over these problems.